In this section, we will mainly talk about the various definitions and notions of fairness, how do they relate to healthcare, and the various issues, trends, and controversies related to how they're applied in the context of healthcare AI. But before we talk about definitions, there are a few foundational concepts that need to be defined first. We will start with these. Here's a quite interesting quote from Frank Pascal, that is, how we are categorized through data affects how we will be treated. In the context of fairness, what that means is that the notion of fairness that we're going to use will also define how we determine if something is fair or not. One of the foundational concepts in this context is discrimination. According to the Oxford Dictionary of the English Language, discrimination is the unjust or prejudicial treatment of different categories of people or things, especially on the grounds of race, age, or sex. Two types of discrimination are widely recognized: disparate treatment versus disparate impact. Disparate treatment, or intentional discrimination as the name suggests, mainly depends upon the class membership. That is, a person is being discriminated because they belong to a certain class, where the class could be, let's say, race, sex, ethnicity, religion, etc. As an example, consider the following. Suppose there's a population who has a certain disease, let's say acute coronary syndrome, and then we discover that because of some bias, there are differences in the treatment of that particular disease across populations. Disparate impact, on the other hand, corresponds to unintentional discrimination. That is, the treatment appears to be neutral, but it impacts the protected class. As an example, consider the following. Suppose there are certain policies related to hospital relocation, access to care, which on the surface is neutral. Every person, every group is supposed to have equal access to it. But when we do the analysis, we realize that it's mainly the minority populations who are being predominantly affected by those policies. This, however, does not mean that different groups should always be treated in the same manner. In fact, there may be scenarios where the opposite may be true. That is, in order to maintain fairness, one may actually have to treat different groups differently. Such scenarios are confronted by human clinicians on almost daily basis, and they address these mainly a case-by-case basis, which also means that it may not be scalable in the context of algorithmic decision making. Additionally, there's an element of subjectivity across clinicians while making such assessments. To illustrate, we shall use the example of patient no-show prediction. This problem or scenarios corresponds to the problem of predicting if a patient is going to show up for an appointment or not. This is a real-world scenario that we have encountered ourselves. So in this example, suppose there is a hospital system in the Midwest where we have to predict on a daily basis which patients are going to show up and which are not going to show up. And then we observe that the model has sufficiently good performance across different cohorts, let's say across different ethnicities. So one way to look at this problem is that once you have built a model, have sufficiently good performance, then your job is done. But once we start teasing apart the distribution of positive, false, or true as well as false positives and negatives, we realize that the overwhelming majority of the people who are predicted to not show up belong to various minority populations. And then from that we realize a few more things, which is that it's not the case that these vulnerable groups they are intentionally missing these appointments because they do not want good healthcare. It's because if you look at the timings and the location, then the hospital or the healthcare facilities, these are much farther away from where many of these minorities live. The public transportation is not very good. A lot of these people do not have access to vehicles. uh, many of these people, they also are unable to take time off from work. Um, and additionally, many of these uh, actually have to take care of um, other folks. So, for example, there may be a primary caregiver for an elderly parent or for a child. So the time in which they can show up, so that is limited. In contrast, if you look at other groups, then let's say um, mainly because of their vocation and socioeconomic status, it's easier for them to take time off, having access to transportation, so on and so forth. So the problem being that a machine learning problem now becomes a larger socio-technical problem. That is, we have to look at the outcome, in this case, reducing no-show, not necessarily just from the perspective of building a machine learning model, but from the perspective of how do we improve the outcome. Building a model just becomes one small part of addressing this problem. So in this particular use case, how the problem was addressed was that instead of the patient, in this case, these vulnerable populations, having to go to the clinic or the hospital or the clinic can go to them. So, for example, having mobile clinics, providing transportation on a regular basis to the hospital or other medical facilities. So that can reduce the no-show. The net effect being that if you look at the longer term health of a community, so looking at this problem from the perspective of population health, then that does lead to positive outcomes. Now let us consider an example of differential treatment by race. Suppose there are two patients, James, who is a 65-year-old black male, and David, who is a 65-year-old white male. Both of them have coronary artery disease. Suppose both of these have same or similar symptoms, so they experience chest pain and shortness of breath and are rushed to the ED by their spouses. Both are seen by the same emergency department physician and are both diagnosed as having an acute myocardial infarction or a heart attack. Now, suppose for the sake of illustration, we assume that all the other clinical factors are the same between these two patients. And yet we see that the clinical recommendations and interventions offered are different, and James is treated less aggressively as compared to David. So one question that arises is, how do we determine if the two patients are treated fairly? If we look at the history of medicine and even a large number of recent examples, we do observe that because of unconscious biases and other structural problems in the system, James may be treated less fairly as compared to David. And it is precisely along such scenarios where AI and machine learning offers the possibility to reduce the impact or the difference across different cohorts, different individuals. So we have already talked about vulnerable populations. In the context of protected classes, these correspond to vulnerable populations, that is, they should not be used in decision making. So the table that we see over here lists a number of protected classes. So which basically means that in decision making, there should not be any discrimination or information used, which leads to discrimination on the basis of these variables. So these could be age, sex, race, ethnicity, insurance status, so on and so forth. Another thing to call out over here is that even while these variables are not used, it may be the case that there are many variables of interest which correlate with these protected classes. So, for example, it may be the case that certain types of disease conditions are more prevalent in one population as compared to others. To address such scenarios, many researchers have in fact proposed methods to identify and mitigate proxy discrimination. That said, it is also important to call out that the use of such variables is not always considered illegitimate in certain domains and use cases. So, for example, if you are hiring a physician, then discrimination on the basis of educational qualifications makes sense, but not on the basis of, let's say, age, race, sex, or ethnicity, and so on and so forth. Another important issue when it comes to measurement of fairness is with respect to the model performance in general. So there are a number of scenarios where that becomes important. So for example, if we have, let's say, a limited set of features for certain populations, then that may lead to differences in model performance. If you have skewed distributions, it may have the same effect, limited data availability. And additionally, once we have built the models, then uh, we should also look at the distribution of errors across subpopulations. So for example, it may be the case that we have multiple models which have same reported accuracy uh, or even precision recall AUC. But if you look at the distribution across different populations, then it may be the case that the error is distributed differently. So just looking at the overall predictive performance, that may not be sufficient to determine which models should be used if you're concerned about fairness. Another place to focus on is understanding disparities in predicted outcomes. By that, what we mean is that suppose we have a predictive model which does well on the prediction task, then we should look at how the results are different across different vulnerable populations. Are there skewed proxies which are being used? Are there external processes which are not captured in the data? So one example of that is the no-show prediction problem that we described a few slides ago. So to generalize these issues a bit further, we can put these into four main buckets. So when it comes to measuring fairness, then we can ask, what are the different ways to measure fairness? Uh, in terms of the predictive performance, how well is the model performing across different cohorts? Uh, how good is the model calibrated? And once we have built the model, so the question to ask post-deployment is, uh, how are the insights from the model being used to intervene? How are the resources being allocated? Now in this section, we will now zoom out and describe various notions of defining and measuring fairness in general. The first notion of fairness that we shall focus on is fairness through unawareness. That is, a model or a predictor achieves fairness through unawareness if the protective attributes are not explicitly used in the model. It may be the case that there are certain variables in the data that can be proxies for certain protected variables, let's say sex, age, ethnicity, so on and so forth. In other scenarios, it may require that we have to use the protected variables in order to avoid discrimination. That is, discrimination may be needed in order not to discriminate. Because of the presence of proxy variables, and it may not be possible to eliminate all types of proxy variables, one researcher has even stated that there's no such thing as fairness through unawareness. The second notion of fairness that we address is demographic parity. It is also known as independence or statistical parity. The main idea is that the proportion of each protected class should receive the positive outcome at equal rates. It is inspired from what is known as the 4/5 rule in the legal domain. According to a code of federal regulations dating from late 1970s, a selection rate for any race, sex, or ethnic group which is less than 4/5 or 80% of the rate for the group which the highest rate will generally be regarded by the federal government agencies as evidence of adverse impact. And so this particular federal regulation becomes the foundation for demographic parity. It's often used to audit models for disparate impact, and one of the reasons why it's widely used. And we can ask the question, when should one use demographic parity? So where the intention is that one wants to change the state of our world in order to improve it, also to remedy historical biases that may have affected the quality of our data, prevent the reinforcement of historical biases. Another widely used notion of fairness is what is known as equalized odds. The main idea is that we are trying to match the true positive rates and the false positive rates for different values of the protected class. Consider the following formulation. Suppose you have a binary classifier C with classes X and A and a target variable Y. So we can formulate equalized odds as the scenario where C is independent of A, conditional on Y. In many real-world scenarios, this particular formulation may be too restrictive, and so a relaxed version is often used, which is called equality of opportunity. Here, the idea is that we are trying to match the true positive rates for different values of the protected attribute. Instead of matching both the positive rates and false positive rates for equalized odds. One question that arises is, when should we use equalized odds? In scenarios where we want to ensure that the accuracy or the predictive performance is equally high in all demographic groups, uh, and we do that even to the extent of punishing models that perform well on the majority group while doing not so well on the minority groups. In terms of nomenclature, equalized odds is also known as separation or positive rate parity. Yet another notion of fairness is predictive rate parity. It's also known as sufficiency. So using the formulation that we just described, so we can formulate predictive rate parity as Y is independent of A conditional on C, basically satisfying both the conditions given here. So predictive rate parity is achieved if the positive predictive values or rates across the different groups are close to one another. So we can ask our standard question, when should we use predictive rate parity? In scenarios where it is less important to balance across different demographic groups, in scenarios where differences in model performance across groups does not lead to discrimination. The last notion of fairness that we are going to consider is counterfactual fairness. Here we measure fairness from the perspective of causes of the bias. So we consider scenarios where, let's say, a counterfactual value replaces some original value of the attribute of interest or the protected or the sensitive attribute. That said, it comes with a number of presuppositions. So it supposes that we have some sort of causal graph that describes the underlying process. We know how it looks like, which features should be used, and what is their relationship. In practice, it is extremely difficult to do so. Individual fairness is another notion of fairness. The main idea is that similar individuals should be treated similarly. It's a relatively straightforward way to define fairness and also measure it. The main issue is that defining what constitutes similarity and across what attributes. Because different stakeholders may have different ideas regarding which appropriate metrics to use uh, to define fairness and which of the features or attributes constitute the most relevant parts of defining similarity. This particular table summarizes the various notions of fairness that we just described, their mathematical formulation, motivation behind that particular notion of fairness, and its flaws. Given that this is not the main focus of our tutorial, so we will not delve into too many details regarding these. That said, a few callouts are important, especially with respect to the flaws which may be associated with these. As we described earlier, with respect to unawareness bias, even if we remove the protected variables, it may be the case that there are other highly correlated features which can be proxies for sensitive attributes. So, for example, a good proxy for race in certain locales may be the neighborhood in which the patient lives. With demographic parity, it may be possible to create classifiers where, let's say, consider the scenario of hiring a set of cohort. If we hire the qualified groups from one group and random people from the other group, we can still achieve parity. For equalized odds, it may be the case that uh, if we use this particular notion of fairness, then we may not be helping in closing the gap between two groups if that is the end goal. And lastly, counterfactual is very ideal. In practice, it is very hard to operationalize. Lastly, we note that demographic parity, equalized odds, and predicted rate parity are collectively known as the group notions of fairness. In this section, we shall now talk about different impossibility theorems of fairness. These are mathematical results which show that certain desirable conditions when it comes to fairness are just not possible in the real world. This has real-world implications and consequences for how we think about fairness in machine learning models and how we operationalize these models. The most well-known theorem of impossibility theorem of fairness can be stated as follows. That is, no more than one of the three fairness metrics of demographic parity, predictive parity, and equalized odds, also known as group fairness, can hold at the same time for a well-calibrated classifier and a sensitive attribute. In other words, it means that all three notions of group fairness cannot be satisfied simultaneously. Another way to describe this is that it is impossible for a single data generation process to satisfy all three group fairness metrics. This theorem has very strong practical consequences that given these multiple notions of fairness, and in an ideal setting, it may be the case that we would want to satisfy all three. It is just not mathematically possible to satisfy all three at the same time. So for particular use cases, we have to define or pick and choose which particular notion of fairness should be satisfied and to what extent. To illustrate the impossibility theorem, consider the following example. Suppose we have two groups with different outcome rates. A predictive test can have consistent error rates or consistency calibration, but it cannot have both. In this example, the results are given using coarse prediction scores. They are thresholded to divide the population. Let's say the population is n equals 100, and we divide that into low and high risk cohorts. Also given are confusion matrices for a low prevalence group with, let's say, 20% outcome rate, that's matrix A, highlighted in red, and a prevalence group with 30% outcome rate, so that would be matrix B, highlighted in green. So these are given. For the low prevalence group, in this case, a predictive test with an 80% sensitivity and specificity identifies a high risk cohort with an outcome rate of 50%. That would correspond to your positive predicted value, and a low risk cohort with an outcome rate of approximately 6%. So in this case, however, if we examine the matrix B, the same sensitivity and specificity that we are observing in the higher prevalence group gives rise to outcome rates of 63% and around 10% for the high and low risk cohort respectively. So what does that mean? So this means that it violates the criteria for test fairness because the meaning of positive or negative test differs across the two groups. Okay. On the other hand, if suppose we decided to hold risk cohort specific outcomes rate constant, that would require a higher sensitivity and lower specificity, so corresponding to matrix C. That scenario would violate the fairness criteria as described by equalized error rates. So for example, the false positive rate would almost double from 20% in the low prevalence population to, let's say, around 39–40% in the higher prevalence population. This just illustrates that making the two conditions satisfiable at the same time is just impossible. Another interesting theorem is the impossibility theorem of privacy and fairness. It states that it is not possible for a classifier to have differential privacy and satisfy group fairness conditions. First, it was shown empirically by Kupam and others that for multiple settings and using census data to which they had added noise, they demonstrated that how adding noise to achieve differential privacy can have adverse effects for fairness for minority groups. And later it was shown that this result also has theoretical grounding. Yet another result is that it is impossible to satisfy any major conditions of calibration and fairness simultaneously. So consider the following major notions of calibrations. Group calibration. Suppose we have multiple groups, and for each group and for each bin corresponding to a particular score, so we are talking about standard notions of fairness, the expected number of people from, let's say, group T and B who belong to the positive class should be with respect to a particular fraction of the expected number of people from group T assigned to B. With respect to fairness, there are two simple notions of class balance. So negative class balance requires that average score associated to people across groups belonging to the negative class should be the same. And similar formulation for positive class balance. To illustrate, consider the following example. So suppose our use case is that we want to know the risk that a person is, let's say, carrier for a disease X. And we also observed that a higher fraction of women than men are carriers. This would also imply that our results may indicate that in any test designed to estimate the probability that someone is a carrier, at least one of the following undesirable properties must hold. The test probability estimates are systematically skewed upwards or downwards towards at least one gender. The test assigns a higher value risk estimate to a healthy person, so in this case, a non-carrier in one gender as compared to the other, or the test assigns a higher risk estimate to carriers of the disease in one gender than the other. So this basically means that there's a trade-off in modeling, but that's not a real trade-off in the world. It's just an observation, a fact of the real world. In the next section, now we shall talk about measurement and different types of biases. We start our discussion with data biases. So these may be familiar to the audience from Stats 101. So we'll just give a very high-level description. So sampling bias or selection or various types of selection bias can happen depending upon how data is collected or sampled. Survivorship bias corresponds to scenarios where the data or analysis is concentrated to instances or in this case patients which survived a particular scenario or condition. So just focusing on those and not focusing on those that did not make it. Simpson's paradox refers to scenarios where a particular pattern holds when one disaggregates the data, and another pattern or its reverse holds when one looks at the data in an aggregated manner. Cause-effect bias is essentially causation and correlation. So correlation is not causation. And there are many other types of biases that we encounter. So there's evaluation bias. It could also be in terms of the particular metric that we are using. So misapplying a particular metric to make things look better than they are. So for example, only reporting accuracy but not precision, recall, or F-score. There's there's bias in terms of how outliers may skew the results, response bias in terms of how participants respond inaccurately or falsely to questions. And beyond that, there are a host of other cognitive biases which are beyond the scope of our current discussion. We just wanted to lay these out to recognize that these different types of biases may affect decision making and also may lead to unfavorable or biased outcomes. Another important thing to call out is that most discussions on biases and measurement of biases, especially in the context of AI and machine learning, either concentrates on model performance or just concentrating on the models and beyond that allocation of resources or services. But in reality, the thing that we are most interested in are the clinical outcomes. Um, so from a clinical perspective, we look at uh, equality in terms of outcomes, performance, uh, allocation, reduction of variability, and how patients are handled, services that are provided, so on and so forth. Another very important thing to call out is that in the context of healthcare, these biases are not siloed, they are interrelated. And different biases are likely to affect different parts of the machine learning workflow. Uh, so, for example, how the data is sampled, that may be most relevant to when the data is collected, how the model is built. But beyond that, there are certain types of biases that in general people tend to focus less on. So think about privilege bias. So in this context, what that means is that just think about the model data collection part, patients which are served by the model and patients which are not served by the model. So how does that affect the outcomes? And then that gets fed back into the machine learning model. If there are disparities, then they can get exacerbated. For certain protected groups or vulnerable populations, it may be the case that we do not have sufficient data or the data is bad quality, so that may also come into play. Once the data is, or rather the model is operationalized or deployed, then an end user has to interact with the model, so there's automation bias that after a certain amount of time or certain usage, the end user may start relying on the model too much uh, and overruling their own judgment. There's dismissal bias, most famous or well-known example being alert fatigue, that, and not just limited to machine learning, that if you're getting too many responses or too many callouts from a electronic system, then you may just start ignoring these because too many alerts, too many pings, so on and so forth. In this section, we shall now talk about various trade-offs of applying fairness in uh, healthcare ML. So the first trade-off is fairness versus performance. So if you really think about it, then the predictive performance of a model depends upon the data, the algorithm, the hyperparameters associated with the model. In general, it has been proposed that fairness negatively impacts performance because it diverts the objective from accuracy only to both accuracy and fairness. So there's, in terms of the objective function, so it's not just one thing that we are trying to optimize, but now we are trying to optimize two different things. Uh, there are also trade-offs present in terms of different notions of group fairness in conjunction with model performance. So that may also play into how we are choosing which particular notion of fairness to use. That said, we can define these trade-offs in terms of, let's say, an optimization problem so that uh, it's possible for us to derive theoretical results and describe the limits of trade-offs whenever possible. Along the similar lines of reasoning is the fairness versus explainability trade-off. But interestingly, the relationship between interpretability and fairness is much more complex. Some studies have shown that the relationship follows four different trends depending upon the correlation between protected, non-protected attributes and class labels. On the positive side, it has been observed that interpretability or explainability fairness trade-offs do not depend upon group imbalance or class imbalance. Uh, Another interesting result is that global Shapley values can be interpreted as each feature's marginal contribution to the overall demographic disparity in the model. So in other words, the shape framework used for explainability can be modified to explain fairness. And in the context of fairness versus explainability, we see somewhat of a paradox. So the explainability of machine learning models intends to bring about greater scrutiny of models, and so the possibility of fair and equitable models. However, that may require creating simplification of models to make them more interpretable. And if that's the case, then, well, that may bring about performance degradation and less fair models. Uh, and so hence the paradox. Uh, and so in general, the recommendation is that if one has to choose what to optimize for, then it's a four-way trade-off between fairness, performance versus explainability versus risk. The risk is defined in terms of the outcome of interest. So for example, let's say the risk associated with making a decision related to a model for predicting risk of mortality. Let's say the decision could be that whether to do a certain procedure or to send somebody to hospice care. So these are critical decisions versus, let's say, for a general ward, determining the number or predicting the staff needed. It may not; these concerns may not be as important. So it, as a general guideline, it the answer to this trade-off would depend upon the particular domain uh, and the use case of interest. That said, there are certain results which have shown that existing explanation models like Lime Shape, they are not really suited for fairness. So the manner in which these authors demonstrated this was that they retrained a model with an additional penalty term corresponding to the influence of the predicted variable. And what they observed was that the explanation for that feature can be suppressed without substantially affecting the model predictions. And so one of the conclusions from that paper was that feature importance of the protected attribute may actually be a poor measure of performance. Now, putting some of these things together, we come to another paradox. If you look at one of the ethical principles that guides healthcare in general is beneficence. That is, providers must or clinicians must do everything that they can to benefit the patient. But we just observed that removal or reduction of bias could possibly reduce predictive performance and thus, from a global perspective, undermine the principle of beneficence. So the challenge that one needs to address is that how do we simultaneously reduce bias and maintain satisfactory model prediction performance while upholding beneficence?